But probably. Thank you. Taking it to heart, I see. The pack idea. All right, so straightforward Q-learning turns out not to be, did I say what pack? Yeah, that was the previous slide. So are there algorithms that do this? Well, the algorithm that's sort of most commonly studied in RL doesn't really. Which is not entirely fair for me to say, because Q-learning isn't an algorithm, it's actually a family of algorithms, and people haven't analyzed all possible members of this family, because it's sort of infinite. But most of the ones that are in common use have been analyzed, and they don't fit this criteria. And the reason for it ends up being this kind of task here. It's called the combination lock. So here's an environment. This is an MDP with states and arrows of the actions. There's a black action and a blue action in each state. All these states have 0 reward except for resetting back to the start, which gives a slight positive reward. But way out here, there's this thing that gives very high reward. Relative. I don't know, 20 watts. $20 billion. Yeah, that's very high reward. 20 units of happy. So if it makes it all the way out to here, it can actually gather a lot of reward and be very happy. But all along the way, while it's exploring, all it's seeing is that, blue actions seem to be really good. Like it wanders out on the chain and tries a blue action. Oh, that was good. Oh, it was good. Actually, I can get it sooner if I just keep doing this. And so it ends up sitting, what Q-learning tends to discover is just sitting here and doing this. That's provably true. If you initialize the value, the Q value is low, and it uses a kind of random exploration that says, when I'm in a state, choose the action that I think is best, except for with probability epsilon, just try something random.
Don't you have a self loop on the first thing?
Sure, let's put a self loop on the first thing, so it'll do that. Yeah. And yeah. So what happens here with epsilon greedy? So epsilon greedy is the standard thing that people use, and it's sort of embarrassing. So what it does is, each time it's in a state, it looks at its current estimates, and it says, whichever action is best, take it. Otherwise, try something at random. And there's 2 things about that are bad. One is, in the beginning of learning, it's believing its values way too much. Probability 1 minus epsilon, it's following what it thinks is best, but what it thinks is best is complete random garbage in the beginning. So who knows what it's doing in the beginning. Then, once it starts to really know what's going on, it has the following kind of behavior. Let's say it even knew that way at the end of this chain is the 20. So it's marching along, yeah, that's the best value, that's what, uh-oh, time to explore. Back to the beginning. Duh! So imagine sort of going through life like this, or walking on a tightrope or something like that. It's like, time to explore, no! And it's off. So epsilon greedy is really irritating as an exploration algorithm. And it's very weak. It's very simple. You can just slap it on top of any algorithm that's choosing actions, but it has this sort of problem. Is that a common impression? All right, so we can't just count on randomness to balance out here. We're going to have to be a little bit smarter. And a model-based approach does give us a nice way to do this. So let's look at the chain example again, the combination lock example. And let's imagine that we've explored most of the world, except for that really happy state at the end. So what does a model-based approach do? It builds this MDP, and it chooses actions optimally with respect to its best guess. It's built MDP about how the world actually works. But it doesn't really know what happens. It's never taken this black action. It's only taken the blue one. So it doesn't know what the black one does. So what should it do? Well, it can assume that what's out there is really good. It can assume that what's out there is really bad, or maybe it could be the average of everything that it's seen so far. But in this case, it really should, all that matters is it assuming something high or something low? So we'll build a little 2x2 diagram here that it's either going to assume low or high for what's out, the unknown. And the truth of the world is either that it's low or high. Okay, so just qualitatively, bear with me for a second. What are the different outcomes in these 4 cases? So if it assumes low and the truth is low, then it's not going to bother to go out there. It's just going to do Franco's self loop over here and not even bother going and discovering that it's wrong. But that it was right. But that's okay. That actually is the optimal thing to do. So that's a good case. On the other hand, if the truth is that there's some really huge reward out there, it doesn't think that. It doesn't go check. It just stays here and does the self loop forever and never discovers that it's wrong. So that's a really bad case. That's not pack MDP. It's not choosing actions near optimally forever. Right? It's not there's no bound anymore. It's infinite. So that's a bad case. On the other hand, if it assumes that what out there is really good, but it's wrong, it's actually very low. Like, oh, I've never tried that before. I bet it's fun. Oh, it's not fun. What's going to happen is the policy is going to push it all the way out here. It's going to get to the question mark and go, darn, I really wish that was better than it was. They say it gets reset back to the beginning. And it got stuck in there if it was a good reward. Oh, if there's a bad reward, yeah, it gets stuck in there and it just suffers forever. But that's okay, because after that, all its actions are near optimal. Beyond that point for a second, if the truth is that it's really low, but it assumes that it's high, it will go out there and get near optimal with the end reward. If it assumes that it's high and it really is high, then it'll go and visit it and find out that it really is optimal. That was the right thing to do, and that's all good. So of these two choices, this first one is not pack MVP. It doesn't actually get near optimal reward in the case where it assumes something pessimistically. In this other case where it sometimes makes a mistake by thinking the world is rosier than it is, it could be pack MVP. I haven't proven it yet, but it could be pack MVP as long as it's not doing too much exploration. Because each time it's doing exploration, those are suboptimal actions.
So I think that
there's an asymmetry.
Your answer to Anna's point is really relevant here. If your objective were to maximize your expected discounted reward, you'd have a different.
That's right. So this pack MVP criteria was chosen sort of carefully.
Yeah.
It's not that we're not interested in it. It's just provably not achievable.
Right?
Because if you're allowed to shoot yourself in the foot and then pay infinitely bad forever, then there's no algorithm that can actually solve this. Right? Because the unknown is either really good and you need to check it out, or it's really bad and you're going to pay for it. It's unsolvable. What's that?
Road lines.
Yeah, IEDs and stuff. But pack MVP doesn't.
But you could also
mind that. Yeah.
The exploration, I mean, where that question mark is, could be an enormous network of sort of lukewarm stuff. Right?
Yeah.
So you really want to be cycling around in here where you're getting at least some reward.
Well, so if there's a big network here, it's not bigger than the size of the state space. For some amount of time, it's going to explore it and eventually decide that it really was not a good place to be.
State space. I guess my point was that you need to compromise because it's not possible. But there are different ways of compromising. One is to take an objective function that's actually achievable. Another is to assume some additional structure on the input instance.
Right, so both of those are completely valid, and we use them depending on the situation.
Yeah. Okay.
We'll talk more about assumptions later, but the field has focused very much on these kind of general MVPs. In fact, you get papers rejected if it looks like it's too specific. So we have been trying to handle the general case, but in our experiments, we often will add in the kind of knowledge that's necessary, because these are they end up being fairly weak algorithms. They do a lot of exploration. All right, so the main idea here to make this work was this notion of optimism under uncertainty, that the algorithmic idea is that we're going to learn either the Q function or the transition reward functions. We're going to distinguish known from unknown states in the world or outputs that we can take. We're going to treat things that we don't know about as if they were good, assume a rosy possibility, and that will drive exploration, at least until things are learned well enough to learn, okay, that wasn't so good, I'm not going to do it anymore. So I sometimes think of this as the Pangloss assumption. You've read Candide.
Isn't it the wrong literary? I mean, you're assuming that better out there.
That was a criticism I wasn't expecting. Yeah, go ahead. Something else is better. No, we think we're in the best of all possible worlds. That's the reference. Because the way out there, there's some high. It's possible that there's a big high reward, so there is a high reward.
Okay.
There may be other good ones. We can talk about that.
No.
I actually even wrote it on the slide. So either you're right and nothing's lost, or nothing much is lost, or you're wrong and you discover that world isn't really one of the possible worlds, and so you actually improve. So connecting this back up with machine learning, the main thing that we're going to try to do is learn either the Q function or the transition and reward function, but we need to learn it in the right way. And so let me say what some of the wrong ways are from the literature, and then I'll explain the way we've been doing it in our lab, the new model that we introduced. The old good for other things but not good for reinforcement learning models are, first one is PAC. So this is Valiant's initial model, and that says what we're going to do, these represent examples of, say, transitions in the environment. For a while, we're just going to collect data. These blue boxes represent labeled data, experience. And we're going to have a couple experiences until we know things well enough, and then we're going to use that to actually make correct predictions after that. Okay? And so the PAC model says that if these inputs are drawn from a fixed distribution, and we get to observe labels for some of them, we need to be correct on all future examples drawn from that distribution. If we can achieve that goal, it's called a PAC learning algorithm. Not PAC MVP, but just PAC in the standard classified learning setting. The problem with this is if we learn our transition and reward function using a